looking for distributed consensus, making the impossible possible, you are not in the wrong room. I changed the title of the talk, but the theme of the talk is very much still how do we achieve consensus, something which, in theory we can show under certain conditions is impossible, but in practice we do manage to achieve it, even if we don't manage to do it in a very performant way. So, my name is Heidi Howard. I'm a PhD student in the Systems Research Group at the University of Cambridge, and I'm going to be talking about flexible Paxos. Flexible Paxos is a simple yet very widely applicable result about distributed consensus. I did this work at VMware Research in collaboration with Dalia and Sasha. This consensus is famously a really tricky area. It's something a lot of people have difficulty with, and I'm going to be trying to explain some of those subtleties today. So I'm really happy for people to put their hands up and to interrupt me with questions during the talk, and I've made sure that the talk is short enough so that we can do that. So I'm going to be talking about flexible Paxos. There's a website there if you want to look up any of the resources. The slides for this talk are there, as is the paper. So when I say distributed consensus, these are the kind of projects that often come to people's minds. And I think most of you will recognize at least one or two things on here. We have things like Zookeeper, which is a tried and tested system that uses distributed consensus underneath. And then we've got newer things like Log Cabin, which is the reference implementation for Raft. We heard from earlier today from CockroachDB, and people have been talking about Cassandra, which some of their components do use consensus underneath. Then we've got container orchestration solutions. So these are things like Kubernetes, Docker Swarm, and Mesos that also use consensus. Now, whilst this is a really broad space of open source solutions, the key underlying idea behind these things all come from this paper. So this is Part-Time Parliament. This is Leslie Lamport's original paper. It's an experience to read. I'm not going to say it's particularly useful, but it's definitely interesting, and it's definitely a fun insight into something. I'm not sure if that thing is distributed consensus. But to save you reading it, I will say this. Basically, what Paxos says is that when we want to reach agreement over something in a distributed system, we need to get the majority of people on board, and we need to do it twice for the purpose of safety. And I'll talk a little bit about why we need to do that, why we need to have two phases. But the key idea is basically we have a first phase, we often call it leadership election or something like that if we're talking about Raft, and a second phase where we talk about what value we're going to be agreeing over. And in both cases, we need the majority of people to get on board. Whilst this is easy for us to think about, in practice we can see that this isn't very scalable, right? If you have to get the majority of people to agree to anything, it doesn't work very well. And the analogy here is government, right? We don't have the whole population voting on every single decision because that would take a really long time. Instead, we elect someone to represent us, and then they make decisions for us. And sometimes we don't elect them and they make decisions for us. British, Brexit, yeah. So what I'm going to tell you today is something quite new and different. This is work that we've just done. It's just been accepted for publication, and we'll be seeing it coming out in the next few months. And the result is this. We do not need majorities to safely reach distributed consensus. The idea of needing majorities, introduced even before Lamport, introduced by Brian Oakey in '88, has perpetuated this field and has been absolutely foundational for 3 decades. But we have been able to show, formally verified and accepted at a theoretical venue, that we do not need this. This is a big claim, I understand, and I'm going to talk you through the details of it. In many ways, it's a very simple result, but I think it's a really powerful result. And why I'm here today is to kind of share this with you, and I hope in future years we may see people using this in systems. The other thing to point out, which has been a source of confusion, this isn't a new consensus algorithm. This isn't like a competitor to Raft. This is actually orthogonal to the existing things that are there. And you can, and I'm talking with people too, apply this in all sorts of systems, whether that be Zookeeper, Console, Raft, etcd, Paxos variants, etc. You can use it in all sorts of ways. So the purpose of today, firstly, is to understand to actually understand the Paxos algorithm. It's not that hard-ish, but do interrupt me. And then we're going to learn about what is flexible Paxos, how are we generalizing it, why can I make this big claim that you don't need to use majorities when everyone knows you need to use majorities. I'm going to introduce the idea that now that we don't need majorities, there's a really broad spectrum of ways that we can achieve distributed consensus, and from that we can build linearizable and strongly consistent systems. And thirdly, most controversially, I'm going to argue that majorities are not the best and they're not the most practical solution for most systems. So this is a talk on distributed consensus. So what is consensus? Consensus, for the sake of this talk, is the ability to reach agreement in an asynchronous distributed system in the face of crash failures. So asynchronous here basically means real, right? You send messages and they'll get there probably at some point. We can't put a bound on how long that takes. And the same with the machine. You ask the machine to do something, you ask it to write to disk, it'll probably get around to it at some point. We hope it'll be quick about it, but we're not going to put any timing assumptions on that. We don't assume that the clocks are synchronized either in a relative way or an absolute way. In fact, the only assumption we really make here is that the participants in this system do what the algorithm tells them to do. We can allow them for them to not do that. That's a field called Byzantine fault tolerance. And if you're interested in that, I can answer questions about that later on. But for this talk, we're assuming non-Byzantine behavior. So machines act the way that we tell them to. I wish that was true. So people have been researching distributed consensus, Paxos, Zookeeper, various variants for decades and decades and decades. And yet I still decided that I would pursue a PhD in this field. So why isn't distributed consensus a solved problem? Well, firstly, distributed consensus isn't scalable. Typically, when we talk about consensus and we write it in our papers, we say, we deployed a system across 3 machines. We deployed it across 5 machines. We really pushed it. We've deployed it across 7 machines. These kind of numbers are at odds with the practical reality of scalable distributed systems. Secondly, consensus is slow. People have been very quick to rush into deploying Raft in their systems. And people, when this first happened, warned that this is going to be really slow, guys. This is going to take a long time to reach agreement. But people have deployed it, and now people are looking back and saying, do we really need the guarantees of consensus? Like that's taking a long time. You're talking to the majority of people to reach every decision every single time. Ooh, that's a lot of work. When a leader goes down, it takes quite a while for us to get going again. And that leads into the third point here, which is distributed consensus isn't that available. So usually with these systems, we had a system that was on one machine, and then we decided to replicate it so that it would be more available. But in many of these systems, we actually see worse availability when we replicate than if we'd stuck with one machine in the first place, which is pretty sad. In fact, many of the people here will say consensus is just too high a price to pay. We should avoid it. Let's have weaker guarantees. Let's have eventual consistency. Let's use CRDTs. Let's go down that route because this is hopeless. We've reached the end. We can't do any better. So what I'm going to do is I'm going to start by showing you what actually is the algorithm and why people believe there are these limitations. So back in the day, once upon a time, we lived in a world before distributed systems. There was a simple server and some clients. I'm trying to be really abstract and general and explain something here that's used in many different algorithms. So I'm literally going to use shapes in slots to not get into the details of any particular application. So clients come along and they want to interact with this server that's got 5 slots and some shapes. So they're going to add some shapes and they're going to read some shapes. So here we come along. Append the diamond for me. Okay, cool, I'll do that for you. Tell me what's in slot 4. There we go. There's the diamond. All is well. At some point, however, this server is going to fail. Failures are unfortunately inevitable in systems. And the client is going to be left waiting. So, distributed systems to the rescue, everyone. So, let's replicate this. Let's have 3 servers all with this log. And what we're going to do, because we want to keep these in sync and we want to keep them up to date, is we're going to pick one of them and say, you're in charge of deciding what gets done, and the other guys, they're going to be your replicas. So we kind of have one person, we'll say, you're the leader, the master, the primary, the distinguished proposer, you're in charge, and the rest of us will be your backups, will be your followers. So in this scenario, I'm going to take this middle node and say, you're the leader, and the other 2, you're just servers, you do as you're told. So a client comes along and says, hey, I want to append this diamond again. And the leader replicates this to the other servers, gets the response that that's been done okay, and returns to the client. All is well with the world. But the problem here is that that leader waited for both the servers to respond. So if you require everyone to participate in your decisions, you've just got worse availability because now you're 3 times more likely for something to fail. So the question arises, how many copies of that request is enough? If you're a leader and you've said, come on everyone, do this thing, append the diamond for me, how many people need to come back and get on board and say, yep, we're on board with you, we've done this? When can we move on? When is it safe to tell the client that this has been done? Well, we call a group of nodes who have agreed, which is sufficient, a replication quorum. And usually this is majorities. And I'll go on to kind of generalize that in a bit. So in this system where you have 3, you would need 2 nodes, so that's the leader and one of the other servers, to get on board before you tell the client, yep, we've done that, we've appended the diamond for you. And we see a trade-off here, right? The more copies that you want to make, the more resilient you'll be because the more copies of the information that you have and the more failures you can tolerate. But the fewer copies that you have, the faster you'll be. You could go all the way down to having just 1 copy just on the 1 node, and then it would be nice and quick. You don't have to talk to anybody. So what happens when failures occur? Let's say the 3rd server here has failed, and we're using majority, so we need 2 out of 3. So we should still be able to make progress and carry on. A request comes along, again, to the leader. The leader will replicate it to the server, who responds, and the leader replies to the client. Two nodes out of 3 are up. We've been able to handle a failure. All is well. What happens when the node that fails happens to be that one that we said was the leader, the one that was deciding the ordering of things, and the one that the client was speaking with? This is where things get a little tricky. So we still have 2 of the 3 nodes up, so we still want to be able to make progress and carry on with the system. And one of these other guys, they can step up and say, I'm going to be in charge, I'm going to take on this role, I'm going to take this responsibility for you, I'll do this. But the point is, this new leader, can't just start telling clients, hey everyone, talk to me, I'm in charge. Because if you look at the logs, you can see, because they previously failed, they're actually missing an entry there. So it's not safe for them to do this. Before they take over, they've got to do a little bit of work first before they can do this. So it's important to recall that in this class of systems, what I'm trying to do is ensure that we never compromise safety. And safety being when we tell a client, we did that thing for you, we did it. We're never gonna go back on that promise. So the new leader, before they can take over, has 2 jobs that they need to do. Firstly, they need to stop the old leader. So I showed that old leader as having failed, but in practice we don't know whether that old leader has failed. Generally what we do is we kind of poke them, and if they don't answer, we assume that they're dead. But as zombie movies and stuff show us, things may be alive even if they don't respond when you poke them. So we want to make sure they're dead so they don't come back to haunt us in the future. And secondly, we need to learn about everything that's happened in the system before we became the leader to ensure that we don't contradict things that happened in the past. And the ordering is important here. You need to get rid of the old leader and then take a kind of a review of the state of the system before you proceed. If you did it in the other order, you would learn about the state of the system, and the old leader may still be hanging around messing with things. So first thing first, how do we deal with this old leader that might come back to haunt us? Well, a naive solution would be just to ask them to stop. And this is something in many of the newer systems where you actively choose to preempt leaders. People forget. You can just tell them, stop doing that. Although the problem is, if we believe the leaders failed, telling them to stop doing it probably isn't going to work because they're probably not going to answer us. Another thing we could do is use leases. So the leader has some kind of lease, and they're in charge for the 10 seconds. So when that 10 seconds is up, someone else can take over. The problem with leases is they rely on clock synchronization, and especially now that people are moving more towards the cloud and to AWS, in this world where safety is paramount, that's a dangerous assumption to make. So thirdly, what we can do is if we can't talk to the leader, but we want to stop them, we can talk to other people in the system and say, promise to stop talking, promise to stop, promise to ignore them, whatever they tell you, don't listen to them. Recognize me as being in charge. And if you can plant enough people in the audience to ignore the last person and to recognize you as the new leader, then you can take over control. There may still be someone there who thinks they're in charge and thinks they're the leader, but if you've got enough plants there who won't listen to them, they won't be able to do any harm to you. So say say the old leader has died, I am the new leader, I want to take over the world, and I ask you all, promise that you're going to listen to me and you're going to ignore the last guy. The question arises yet again, how many promises are enough? How many people do I need to get on board? Bearing in mind that some of them might be slow, and some of them might be on their laptops, and some of them might have failed. How many of them do I need to get on board before I can proceed? And what we do is we refer to this group as the leader election quorum. So this is the group of people that you need to become a leader, basically. And the idea here is that I need one person from each of the possible replication quorums to be on my leadership election quorums. So that old leader who might be replicating something, adding something to that log, they won't have access to a group of people to do that because I've gone to each of the possible groups and said, no, ignore him, talk to me. No, ignore him, talk to me. So in the majorities case, if we were using majorities for replication, we now need to use majorities for leadership election. So I've got 2 people out of 3 to promise to listen to me, and so the old leader won't be able to do any harm because he has to talk to at least one of those people. There's an overlap here. The other question arises, if I'm going to get people to go around and promise that they're going to listen to me, what happens when I then fail and someone else comes along? We need a mechanism by which people can make promises and also safely break them. And breaking promises is difficult business. So the way that we do this is when you go around and ask people, back me, ignore these previous people, we have some kind of unique value, and how you get that value depends on which protocol you're using, which you use to say, recognize me as being in charge, and promise that you will only ever break that promise to me if someone with a bigger integer, a bigger number comes along. In that condition, you can break that promise to me. But if they have a smaller number, like they're those old leaders from the past, you can't break your promise to me. The other thing we need to do is learn about what's been committed in the past. So safety is paramount here. We can't undo decisions. If something's been appended to the log, we need to know about it. So again, we're going to go around and we're going to ask people, and we need to talk to one person in each of the replication quorums. Now, a difficulty arises here. There may be some requests that are in progress, or some cases where we actually have conflicting requests in a single position in the log. Now, from a safety perspective, we know that only one of these could ever have been successful. And this is where that promising scheme becomes really useful, because we know that people made promises and they only broke them for leaders with higher numbers. If we see 2 conflicting requests in the same position in a log, we choose the one with the higher number, because we know that's the only one that could possibly have succeeded. And that is Paxos. That is the core algorithm. We see a huge number of variants, the most popular of which being things such as Zookeeper, Raft, and ViewStamp replication, but they all build on the same underlying idea. So, I'm not here to give you guys a history lesson. What's changed? Why am I here today? Well, traditionally it was believed that all the quorums, whether you use them for leadership election or replication, needed to intersect. And if you need all groups to intersect, majorities, they're a pretty reasonable scheme. But the fact of the matter is that that isn't the case. We only need the group used for electing a leader to intersect with the group used for replication. We do not need 2 groups used for replication to overlap. And in most protocols, you do not need 2 groups used for leadership election to even overlap. Now, I understand that this is a bold claim, and I'm going to talk a little bit more about it in a second. So what are the implications of this? Well, firstly, it helps us to understand Paxos. I try to teach Paxos to undergrads at Cambridge, and mostly they just nod and then go away and complain. So it's hard to teach people Paxos. And this, if it helps us to understand the protocol, maybe it'll help us to teach it to people and to get it right in the future. For the theory crowd, it's a generalization and a weakening of the original requirements, which is, to those kind of people, it's just neat in its own right. And it's orthogonal to any particular algorithm, and this is really where this work becomes interesting. This isn't a competitor to Raft. It's not a single open source project or a single code base where I'd say, everyone come switch to my thing. It's the newest, the bestest thing since sliced bread. Instead, it's a contribution that changes the way we think about how we reach agreement in distributed systems, and something I think we're going to see realized in a whole host of systems in very different and interesting ways. In practice, the way that we construct quorums can now be different. For a long time, we've thought the majorities were the only way, but what I'm going to show you is there are plenty of other ways that we can do this, many of which are much better in practice. And this introduces a new breed of scalable, performant, and resilient consensus algorithms. You don't have to give up on consensus, because we can do better. So this is what we're used to, majorities. We have a system of 5 nodes, and we require 3 of them to get on board before we can make a decision. And it doesn't matter whether that decision is electing a leader, as shown here in the kind of orangey color, or doing some replication, so adding something to a log. Whatever it is, we need 3 people, the majority, to get on board. And the logic behind this is they're always going to overlap. So the problem with this, as you saw earlier, when I was talking about numbers of nodes, they were quite small, and they were also all odd. So what happens when we have an even number of nodes? What happens if our boss just happens to give us 8 machines to work on? Well, when you need majorities, you would need to speak to a strictly more than half of those machines, strictly half or more. So you can't speak to 4, you would have to speak to 5 to ensure that they overlap. With flexible Paxos, we know that this is no longer the case. So here's an example. Here we have 6 machines. Now, traditional Paxos logic would tell us that we have to speak to 4 of them in order to reach any agreement. And we do still decide to talk to 4 of them when it comes to leadership election. But when it comes to replication, we just talk to 3 of them. And those 2 sets may not overlap, but that's okay. That doesn't matter. And this is, even though it's an improvement of 1, this is really useful. In fact, there's not actually a downside to us doing this. Firstly, it improves fault tolerance because half of the nodes can fail. And if we still have our master, we can still make progress. Secondly, it's faster. We used to have to speak to 4 nodes. Now we can just speak to 3. And thirdly, there's potential here for us to greatly improve the throughput because we have 2 disjoint sets that we can now send replication requests to. So we could send it to the left-hand column, the left-hand side, and then the right-hand side, the left-hand side, and then the right-hand side, essentially doubling our throughput. We can take this further. So as long as the replication quorum plus the leadership election quorum is greater than the number of nodes, then you're safe. Majorities are one trivial way of satisfying this, but there are many other ways of satisfying this. And the important thing to remember here is, traditionally in a system, you elect one node as a leader, and then you do loads of work, tens and thousands of requests, and then the leader fails and you elect a new leader. So leadership election is quite rare, and replication is quite common. So, go ahead.
Sorry to interrupt, but you did say...
Yeah, go for it.
Well, I have a very stupid question, so I don't really understand. You're saying you can write to them, like one group of 3 and one group of 3 separately, but then they'll have like divergent things on them. Like, I'm missing a fundamental understanding of this.
So, no, I don't think I made that clear. So basically, what happens is you've got a leader, and they're trying to replicate some state in the system. They will put something into a log. They're not going to they can't change their mind. They can't send it out and then tell some other people something different. So as long as it's, the leader is doing that, it doesn't matter because they know that it's the same. So those 2 don't have to overlap. If that leader then fails, then you have to elect a new leader, which will see you speaking to 4 nodes. So you will speak to each of those groups, and you'll safely learn what has happened in the past. Any other questions? Stunned faces. So, as I was saying, we can trade off the size of the group that we use for replication and the group that we use for leadership election, because leadership election is much rarer. And here's one example. Here we have 6 nodes. So previously, we had to have 4 of them on board for every single decision. Then I showed that we could just have 3 of them on board. Now, let's just have 2 of them on board. So when we're doing replication, when we're adding things to a log or doing a consistent read to the log, we're just going to talk to 2 of them for each of those, for each time. Then, when we do have a failure and we need to recover a new leader, we're going to talk to 5 of them. So you're increasing the cost of leadership election here and decreasing the cost of replication. The reason why I argue that this is something you would want to do is because replication is so common and is very much in the critical path of your system, and leadership election is far rarer. But what about fault tolerance, right? The reason why we put something on the majority of nodes was for fault tolerance. Well, the reality is now we can handle 4 failures. If we still have the master, we can handle 4 failures in replication. And the system is predominantly in the replication phase. So if we do it statistically over time, we get a higher availability with this scheme than we would with majorities. Any questions at that point? It's a big claim.
Surely the master is the most likely to fail?
The what, sorry?
The master, the leader, is the most likely to fail.
Is that because there's the most load on them?
I would have thought so, yeah.
So I think I can see that argument. It depends. The whole idea of flexible Paxos is, I'm going to show you some other quorum systems as well, is if you're in a situation where your master is most likely to fail, we can actually do some other work that comes with other systems that are better than majorities. So it's about depending on the needs of your system. When I've looked at really kind of high performance consensus systems, they tend to separate the master from the rest of the system and actually deploy that on a machine that is more reliable than the rest of the system, so it's actually less likely to fail than the rest of the nodes. But if masters in particular are likely to fail, then maybe one of the other systems here might be best. Any other questions at this stage? Yep.
Is it something that happens every hour or every week?
I am a PhD student and I feel unable to comment on the realities of real-world systems. From talking to people, leadership election does not seem to be a particularly common in comparison to replication. Should not be.
Yeah, if it is something that's awry. Should be rare.
I feel like many other people in this room are more qualified to answer your question than I.
It was once every few months, and probably it never worked.
This is something that's really funny. So people tend to assume that leadership election is a fairly lightweight process when they're using something. And I spoke to people kind of at the beginning, and I was like, it's going to be really expensive. And they're like, no, it's going to be fine. And then a couple of months later, they're like, it was really expensive. Our system was down for a while whilst it was like transferring all the state. And I was like, yeah, I know, I told you. So the claim, and here's another example with some slightly different numbers. So here we have a replication quorum size of 3 with a total system of 8. The claim here in these particular examples is that if your leadership election is rare, that this is a trade-off that you're probably willing to make. And we can do analysis on this and show that the availability is actually better than it was before. But let's take this result and start to do some things that are a bit more interesting with it. So even though when we're modeling this in theory, we say, oh, all nodes, they're equally likely to fail and will fail independently. Now, anyone that works with systems knows that failures aren't independent, right? One thing breaks, other things break. Failures are very much dependent. If 2 machines are in the same rack, it's more likely that these guys are going to fail together. They don't fail independently at all. So this hand-wavy thing of saying, oh, we'll assume that only the minority fail, and then it will be fine, I don't think that's actually a fair assumption in a lot of systems. So if we know that failures aren't independent, let's not treat the machines themselves as if the failures are independent. They're not equal, so let's not treat them equally. So here's an example of a system. we see the system here has 13 nodes, which is big for consensus standards. This is really very large. So it has 13 nodes, and we've got two examples, one here and one here. And what I've done here is draw these groups, which basically represent, for example, a rack. So a group of nodes where they're more likely to fail together. So what we can say is when we're doing replication, let's get one machine on each rack to have a copy of what's going on. So let's spread that across the system. First thing to note here is this is good in terms of fault tolerance, if we think that machines in the same rack are more likely to fail together. Secondly, this is nice because we're just talking to 4 nodes in a system of 13. If we were using majorities, we'd need to speak to many, many more. So then when your master does fail and you need to elect a new one, we just need to get one rack, which will be easy to talk to because they're going to be close, so low latency. Just need one rack to get on board, and they will have a copy of all of the requests, and they will safely be able to become elected as a leader and take the system forward. And again, we're still now here, we're talking to 3 nodes, maybe 2 nodes or 4 nodes, but still far fewer than majorities. So in actually both cases here, we're talking to fewer nodes than the majority of nodes, and it's still perfectly safe. And as I say, 13 nodes is big by papers in consensus standards. So another example scheme, and this one is mostly just for fun, is grids. So let's take a system of 9 nodes and split it into a 3x3 grid. We can say that any column could be a replication quorum. So if we want to replicate a request, we just need column 1, 2, or 3 to get on board with us. And then when it comes to leadership election, we just need a row to get on board with us. Now clearly any row and column are going to intersect, so we're going to meet the requirement that we needed. But this is quite a fun little system because we never accidentally overlap, in the sense that 2 replication quorums will definitely not intersect. And nor will 2 leadership election quorums. So when, for this paper, we were doing model checking, this was the scheme that we predominantly used. And there are a huge host of other things. So the field of databases, to some extent file systems and data replication, had this idea of quorums, particularly they called it read-write quorums, a long, long time before we did. And they've done lots of research into different systems, and we can combine these systems so we can start to say, let's use majorities within the data center, and then when we're looking across data centers, let's use a smaller group, so we only need 2 data centers out of a possible 8, for example. And we can construct grids, and we can do hybrid schemes where we have majorities at the top maybe, and then you have some underlying thing that's using groups or something like that. The fact of the matter is majorities are not your only option. The point of this work is not to sell you something else and say this is the best, whatever system you're using, but instead to tell you that you have the flexibility to use whatever scheme you like. As long as you meet the requirement that a leadership election quorum and a replication quorum will intersect, then it doesn't matter what quorum scheme you use. The reason why I think this is interesting to the community is because the requirements of real-world systems matter. Now, when we talk about this in theory, we say you want to tolerate F failures and we want to minimize the number of nodes, so we use 2F+1. But in practice, people have actual constraints. For example, I want the average request to take so long. I only have so much money to spend on Azure. I want this failure recovery to take no more than this amount of time for this percentage of recoveries. So it's up to systems and communities to decide what trade-offs they want to make. They don't have to take this one trade-off that was offered by Lamport 3 decades ago. So in summary, the only quorum intersection requirement is that between leadership election and replication. However, so we never need to have 2 replication quorums overlap, and for some protocols, they do require that leadership election quorums overlap, but some don't. It depends on the protocol. I can talk a bit more about that in questions. Majorities are not the only option. You have a whole host of options available to you, and that you can choose whichever is the best for your system. You don't have to give up on strong consistency guarantees. You can have a system that's 20, 30 nodes and still run Paxos on it, and this is actually scalable and performant if you only need to talk to a couple of nodes each time you're doing replication. So what's next for this work? I'm talking with various people in various communities to both adopt it into existing systems. So for example, when you have an even number of nodes, reducing the quorum size by 1 to exactly half for replication is something we can really easily add to things like Raft and Zookeeper with very little work. It's literally changing an integer deep inside the protocol. And then the second part of that is building new algorithms that really, really take advantage. How can we really build very scalable, very performant consensus algorithms? Thirdly, I'm working with some people to do a practical analysis of the different quorum systems, and hopefully what I would hope to produce in the end is this kind of a document with the maths and practical analysis that says, given you're running this kind of system, this is the best quorum system for you in terms of availability and performance. And also to give people numbers, right? If this is a configuration people should have access to a table that basically says, do you want 99.9% availability and this average latency, or do you want 99.9999% availability and this average latency? And we're looking at extending this to other algorithms. So Lampolt's original formulation has been built upon and built upon and built upon and branched out into leaderless consensus algorithms, fast Paxos, generalized Paxos, Byzantine fault tolerance. This idea has absolutely perpetuated into all sorts of areas. Now that we know that this isn't necessarily the case, we can now go and do interesting things in all sorts of different areas. That's it. I'm happy to take questions. Otherwise, you can reach out to me by email or on Twitter. Thank you. Questions? Stunned faces.
No one can leave. Must be questions. So I have a question. What was it? This flexible Paxos. Why not just create a new name? Just start afresh with a new.
There was a lot of discussion over this. Naming things is very hard. One of the reasons I didn't want to give it a new name is because it's already a problem we've begun to see where people assume this is another algorithm. They assume that it's a competitor to multi-Paxos, a competitor to Chubby, a competitor to Raft. Instead, it's a theoretical result that works kind of at the foundation to take Paxos and say, you don't have to have it like this. You have the flexibility to do whatever you want with it. So by naming it Flexible Paxos, I hoped that people would recognize it as being kind of orthogonal to the existing algorithms. One of my biggest regrets about naming it Flexible Paxos is that since we initially did this work, it's become apparent to me that a lot of people are using basically consensus and they don't call it Paxos. For example, they use chain replication, which is an instance of Paxos, or they use view stamp replication, which in fact came before Paxos. So Paxos is almost an instance of view stamp replication. So this result actually affects these guys as well. Where majorities is much more pervasive, but we called it Flexible Paxos. Can't go back now.
Just got a specific kind of implementation question. In the grid example you showed with the columns and rows, so you've got columns as replication quorums and the rows as leaders. If there's a partition between one of the rows and the other two, so that you've got one group that has 6 that in theory still has a majority of the nodes, but there's now an entire leader election quorum on the other partition, does that prevent any of them from actually replicating until they connect again?
So sorry, the partition is between one column and the other columns?
Between one row
One
and the
row
other.
and the
Because
other
in theory,
rows.
that both sides then have a leader election quorum, so they can both elect leaders, but they can't replicate because there's no replication quorum. So is it then
Yep.
not available until that partition
So-
comes back?
In this slide, that would be unavailable, as you say. One of the things to note here is, generally speaking, I'm not going to go into the details of dynamic membership and how you actually go about changing quorums and kicking nodes out and bringing them in. But generally, if we can form a leader election quorum, that means we can recover the state of the system, and we're then in a position to reconfigure the system and basically kick that row out if we want to continue to make progress. If we're in a position where we can own, so if by contrast we lost a column, so we were able to replicate, we could keep going for a long time until the leader fails, but then when the leader fails, we would then be unavailable.
So in this grid example, since you've got non-intersecting replication quorums, if you have a leader election and it decides to go from the left to the middle, so that means the new leader is not part of the original set of up-to-date replicas, how does the new leader find out what the state of the log should have been before then, if it's not part of the old replica set?
So when the new person takes over and they get a row on board, there will be by necessity at least one person from each column there. And since we know how to deal with conflicts, etc., we can guarantee that at least one person will be able to give us the correct answer.
Anyone else?
All right.
Great.
Thank you very much.